Hello, my name is Michael Delaney, and today we are going to be discussing the numerous models that were developed and deployed within RapidMiner that look to predict body fat percentage due to various physical characteristics. The first step to the seven-step business analytics process is the business problem understanding. Now, within this scope, we need to look into why are we trying to predict body fat percentage and why is it important that we do that? Well, body fat percentage is a vitally important health metric that signifies overall health. It correlates with risks such as diabetes, cardiovascular diseases, and metabolic disorders. Now, all this is to say, it is a great indicator of how well someone's internal homeostasis is functioning, and it allows you to gain insight into whether someone is at risk for things such as heart disease or a metabolic disorder. Now, precise methods that measure body fat are exceedingly expensive, time consuming, and often uncomfortable. The methodology behind this can be something as submerging yourself completely in water and being weighed down, having small calipers pinch different parts of fat deposits on your body and getting different pressure readings based on that, and many other things. But these methods are expensive, time consuming, and as I already said, can be very uncomfortable. Now, if the problem is due to those things, it being expensive and etc., then what's an alternative? Well, an alternative is desired. A model that predicts an individual's body fat percentage, which again is based on physical measurements, that provides an alternative to costly and time consuming methods such as underwater weighing. And in the process of showing you this, I will hopefully be demonstrating that a model is able to be developed and deployed that can allow to fix this problem. Now, how do we go about developing and deploying a model in this situation? So first, we need to have a broad data set to build our model upon. So a data set is, in this situation, comprised of physical measurements and body fat percentages from 252 men, and it consists of structured tabular data with numerical numbers only. So there will be no nominal or ordinal data that must be converted into numerical in this situation. It is entirely numerical in nature, which makes it very, very easy to develop a model around this. So the attribute body fat within the data set is the dependent variable or the measured variable, and it is what we're trying to predict. Now, all data is in the following attributes. The data set is comprised of these things: density, body fat percentage, which again is our dependent, age, weight, height, neck circumference, chest circumference, abdomen, hip, thigh, knee, ankle, biceps, forearm, and wrist. And these metrics are all within the metric system. Now that we have a greater understanding of what our data set is comprised of, now we need to decide what data is included in the data set, in the models, and what data should be left out and what should be considered. So all attributes in the previous slide are considered in the model, apart from the dependent variable body fat, with density and abdomen being the two most important features. So how was the model developed and deployed in this instance? Well, it was utilized in a program called RapidMiner, and RapidMiner is a program that allows for the importation of large data sets, and those data sets are then able to be utilized and manipulated in different ways to generate different graphics and gain further insight than the raw data would suggest. So in this instance, we use a specific part of RapidMiner called auto modeling, and auto modeling again allows for the importation of data, but it allows you to easily select what attribute you want to be measuring or predicting, and you're able to just choose different models to develop and test and directly compare through auto model. Now, the generalized linear model stands alone with the lowest relative error. We can see here a screenshot from the auto modeling process has the generalized linear model, or the GLM, at a relative error of 1.2%, with a less than one standard deviation of 0.8%. This means that the GLM is actually very, very precise, especially when compared to the other models. We can see deep learning having an 8.3% relative error, decision tree at a 4.9, and a random forest at 10.5. Now, this is all also taking into consideration the time it takes to spit out these numbers. The GLM does take a little bit more time when compared to a deep learning model. You can see the total time within the deep learning model is 2 seconds, with the GLM being 3 seconds, but realistically, that's a non-factor when considering model deployment, as long as it's not reaching within, exorbitant amounts of time. Now, if the GLM is our best model, why is that? And are there any visual metrics that we can look at to determine that? And the answer to that is absolutely. So here on the right-hand side, we can see the GLM's prediction chart with a 45-degree line, and there are different data points on the line, 252 to be exact, coinciding with the 252 samples of the initial data set. And with the exception of, it looks like 3 individualized points, most of the predicted values fall on or very, very close to the line in this case. The low standard deviation implies a relative uniformity in this case, which makes it much easier to understand and compare these values, as well as understanding that the predictions that they have are relatively well backed due to the other relatively precise results. So seeing here, the GLM also had the lowest root mean square error value at 0.375 compared to the other models, and the other models within the auto modeling process utilized in this report were the deep learning, decision tree, and random forest. We can see deep learning had a 1.903, the decision tree had a 1.646, and the random forest had a 2.181. Now, in this situation, you would, when it comes to prediction models, you want to have as low of an RMSE as possible. That generally implies that there are going to be less instances of the models completely going off of the intended target, which is to accurately and quickly predict the body fat percentages. Now, I would like to take a moment to discuss why the GLM is performing better than these other methodologies. And in my opinion, I think it mostly comes down to the fact that GLM in general is very similar to a linear regression, as you can see by this single line. And linear regressions are very useful when trying to predict numerical data. And as said at the beginning of this PowerPoint presentation, we are dealing with entirely numerical data, and we are predicting a numerical value. In a different use case, if we were predicting heart disease, for instance, where someone is predicted to have heart disease or not to have heart disease based on different physical and medical characteristics, that might be where a decision tree, for instance, is able to have a lower RMSE and would make it a more valuable model, because again, it would be closer to the actual value. It would have more true positives rather than false positives, or etc. Next, we have the model and results communication. So as we can see down here, looking at our GLM predictions again, there are different columns with different color-coded situations that demonstrate which variables or attributes ended up contributing the most towards the predictions, in the sense of providing accurate and precise information. Now, red demonstrates a negative correlation, with green tinted columns representing a positive correlation. So looking at this, we can see 2 immediate standouts. The abdomen and weight categories. Abdomen values contributed heavily towards the green prediction column, which is the 3rd column in this, the prediction, and then the parentheses body fat. And there are some other categories here that contributed heavily, such as ankle circumference, bicep circumference, and forearm circumference, with some different areas not being as useful. So weight itself, interesting enough, was not an immediate indicator of body fat percentage. This could be due to numerous factors, but I think the running theory is that weight is relative to height, and there are many factors that come into considering weight versus height, such as bone density, muscle mass, water weight, numerous things. With all of this being said, in what use case should this model be deployed, and should it in the first place? The GLM model should be deployed into various health and fitness settings to aid in tracking healthy and unhealthy body fat changes. In the scope of dealing with potentially older people who may not have the financial resources or the physical mobility to get into a fully submersive tank to be weighed underwater to get a read on their body fat percentage, something such as this model could provide very, very vital medical insight that could allow their doctors to make more valuable decisions that could extend life or improve the quality of their lives, and etc. And this implementation will allow for greater access to relative body fat numbers, as said, that give greater insight to one's physical and cardiovascular health. And again, there are numerous indicators among the body fat percentages that allow or disallow different potential ailments or diseases, both chronic and acute. With all of that being said, thank you very, very much for your time, and I hope that this was insightful, and I hope that the GLM model that was developed in this could be used to help someone. Thank you.